In this video we will solve this problem. Let us read the problem. Find suitable relations between the angular velocity omega and the two moduli, the storage modulus E1 and the loss modulus E2, for a material which follows a standard linear solid model. Also write the relation between the loss tangent and the angular velocity for the above material. First, let's understand what is standard linear solid model. So in viscoelastic models, we have learned about different types of behavior of the material based on the spring and dashpot. So in standard linear solid model, we assume that the material consists of one spring with a dashpot here, and another spring which does not have dashpot. So there is one dashpot, there are two springs. So one spring and one dashpot are in series. This combination and another spring are in parallel. So this is known as standard linear solid model. So here, for example, when we apply some stress, then this spring will experience stress sigma 1 and there will be some strain epsilon 1, and let's assume that this spring has the spring constant of K1. Here there will be stress sigma 2, strain epsilon 2, and let us assume that the spring constant for this spring is K2. Here the stress will be experienced sigma 3 and strain epsilon 3, and let us assume that the viscosity of this dashpot is eta. Now we can say that sigma 2 is equal to K2 epsilon 2. So this is for this spring. Also we can say that sigma 1 is equal to K1 epsilon 1, and we can also say that sigma 1 is equal to sigma 3 because the stress in this component will be the same. And overall we can say that sigma, which is here, the overall stress is equal to sigma 1 plus sigma 2, or we can say sigma 3 plus sigma 2. So these are the main assumptions of SLS model, and based on this model, the governing equation for SLS can be found as eta sigma dot plus K1 sigma is equal to eta K1 plus K2 epsilon dot plus K1 K2 epsilon. So this is the governing equation for standard linear solid model. So here eta is the viscosity of this dashpot, K1 is the spring constant of the spring which is in series with dashpot, K2 is the spring constant of this side of the spring. So overall this gives a relation of the viscoelastic behavior of polymers using this model. So we will use this as the governing equation for for standard linear solid, and we will apply it to the dynamic loading situation and try to find out the relation between omega, E1 and E2, and also between omega and loss tangent. So we will start with the equation for stress and strain in dynamic loading. We will use the exponential form of the equation as sigma is equal to sigma naught e to the power I omega t plus delta. Epsilon will be given as epsilon naught e to the power I omega t. Omega is the angular velocity, t is time here, and delta is the phase lag. Now, the standard linear solid model, the governing equation is given as eta sigma dot plus k1 sigma equal to eta k1 plus k2 epsilon dot plus k1 k2 epsilon. So here, as we have learned before, sigma dot means d sigma over dt, epsilon dot is equal to d epsilon over dt. So now we will substitute these expressions in the governing equation here. So substituting these equations here, this is a differential of sigma, so we will differentiate here, and after differentiation we will substitute. So this equation will be given as eta sigma naught here, and differentiation of this one gives us I omega e to the power I omega t plus delta plus k1, and here it is sigma, so we will substitute this sigma naught e to the power I omega t plus delta. This is equal to eta, and this is k1 plus k2, and epsilon dot. So here again we will differentiate this one, so that will give us I omega epsilon naught e to the power I omega t, and finally this term plus k1 k2, and epsilon we will substitute this I omega t. So this is the equation, and we will simplify this equation to find out our relation between E1, E2 and omega. So now dividing across by epsilon naught e to the power I omega t, also substituting E star for sigma naught e to the power I omega t plus delta over epsilon naught e to the power I omega t. So as we have explained before, this is a complex stress and this is complex strain, and the ratio of stress to strain is given as modulus, but here in this case this is a complex modulus. So if we do these two steps to this equation, then it gives us eta I omega E star plus k1 E star equal to eta k1 plus k2 I omega plus k1 k2. So now further simplification of this equation will give us E star as equal to eta k1 plus k2 I omega plus k1 k2 over k1 plus eta omega I. Now we know that complex modulus is given as E1 plus I E2, where E1 is the storage modulus and E2 is the loss modulus. So now we will simplify this equation in this form, where so that we can find out E1 and E2. So let's write it again. E star is equal to eta k1 plus k2 I omega plus k1 k2 over k1 plus eta omega I. Now here, as we did in the previous video, we will multiply this by k1 minus eta omega I divided by k1 minus eta omega I. So we are multiplying by the same parameters in the numerator and denominator. So now we can write this as eta k1 plus k2 I omega into k1 minus, so we are multiplying this by k1 here. Now we will multiply this by this one, so here it will be plus k1 square k2. Now we will multiply this to this one minus eta square omega square k1 plus k2, and here we will have I square. Now we will multiply this to this one. That will give us minus k1 k2 omega eta and I. This will be divided by this multiplied by this, which we have already seen before. It is k square plus omega square eta square. So now here we can see that I square is minus 1. So we can further simplify this as plus eta k2 k1 I omega plus k1 square k2 so here I square becomes minus 1, so therefore it will become plus eta square omega square k1 plus k2 minus k1 k2 omega eta I. So now we can see that this one and this one can get cancelled out. So whole will be divided by k1 square plus omega square eta square. So here we will separate the terms with I and the terms which are without I. So we can write k1 square k2 plus eta square omega square k1 plus k2 divided by k1 square plus omega square eta square and plus this part k1 square I omega over k1 square plus omega square eta square. So now if we compare this equation with E star is equal to E1 plus I E2, so we can find that this contains I and this one is without I. So here by simple comparison we can write E1 as this expression k1 square k2 plus eta square omega square k1 plus k2 over k1 square plus omega square eta square. E2 will be given as this part without I, eta k1 square omega over k1 square plus omega square eta square. So now we have found out the relation between omega and E1. And another relation between omega and E2. So these are our equations that we were supposed to find out. And again in this case we can write tan delta as equal to E2 over E1. So E2 is expression here and E1 expression here. So now we will use these equations, these three equations, and we will try to plot the graph between E1, E2, tan delta and omega. So now in this Excel I have taken the values of eta as 0.15 giganewton second per meter square as was given in the problem. K1, the spring constant, is 2.2 giganewton per meter square, and K2, another spring constant, is 0.12 giganewton per meter square. So these are the values given in the question paper. Now we will create some data for different values of omega. We will find out E1, E2 and tan delta according to the equations that we have just developed for SLS. So here you can see for omega 0.1, this is the equation that we have developed, and this is in Excel form now. So after using this equation we can find out E1 as 0.12 and similarly E2 also we can get the values of E2, and tan delta is simply E2 over E1. This is how we can find out E1 and E2 and tan delta. And for now we can write different values of omega 0.1, 0.3, 0.5 all the way up to 1000, and we can similarly calculate all the values of E1, E2, tan delta. We have created the data here, and now we will plot these curves. So here I have angular velocity here and E1, E2 or tan delta. So the values are quite close here, so we have plotted all on one axis, on y-axis, and on x-axis we have angular velocity, but the scale is in logarithmic form here. So this scale is not linear, it is logarithmic scale, and here it is linear scale. So now if we do that, for example, so the E1 value varies in this kind of trend. E2 trend is given here, and tan delta trend is given here. So now, just like any typical dynamic loading graph, we see that E1 starts with low value at lower angular velocity or lower frequency. As we increase the frequency or angular velocity, E1 increases to a very high value and remains there. E2 also starts with lower values, goes to a maximum, and then again goes back to the lower values. And tan delta starts at a lower value, goes to a maximum, and goes back to a lower value. The maximum for tan delta happens at a lower frequency than the maximum for E2. So this is a typical behavior of viscoelastic materials in dynamic loading, which we see for SLS. For the Maxwell, we found that although E1 and E2 follow the typical trend, but tan delta did not follow the typical trend. But in SLS, we see that all the three, E1, E2 and tan delta, follow the typical trend of a viscoelastic material. So we can say that SLS is a better model than Maxwell model.